The Japanese souffle pancake is distinguished by its extreme thickness and characteristic airy jiggle. Compared to a dense, flat American flapjack, these structures stand several inches high, representing a significant shift in culinary scale. Comparing the internal volume of a standard pancake to a souffle variant reveals over 80% of the structure is trapped air, but this air faces constant physical threat. Gravity's downward pull and the pan's upward heat radiation constantly compress and destabilize this empty space. Now, two primary mechanisms drive this collapse. Liquid drainage thins the bubble walls as moisture moves toward the base, while bubble disproportionation occurs as air diffuses out of the high-pressure interior. Preventing this breakdown requires creating a microscopic protein structure capable of shielding these bubbles throughout the entire cooking process. The process begins in the mixing bowl. A whisk applies mechanical force to the egg whites, disrupting the proteins suspended in the liquid. An egg white protein contains distinct regions. One end is hydrophilic, or water-loving, while the other is hydrophobic, or water-hating. In their natural state, these remain tightly curled. The whisk's energy forces these chains to unfold, exposing the previously hidden hydrophobic sections. This model illustrates the proteins adsorbing onto the air-liquid interface. The water-hating ends point toward the air, while the water-loving ends remain in the liquid, creating a cohesive viscoelastic film around each bubble. Excessive whipping eventually snaps this protective layer. The proteins clump tightly, thinning the bubble walls until they suffer a lamellia rupture and pop. Introducing an acid, such as lemon juice, lowers the pH of the mixture. This change in acidity strengthens the protein bonds, allowing the film to remain flexible without clumping. Sugar acts as a stabilizer by increasing the viscosity of the liquid. It functions as a molecular glue that prevents water from draining out of the bubble walls. When the foam reaches the state of stiff peaks, it serves as macro-scale evidence that the microscopic bubble walls have achieved structural integrity. The next challenge is successfully integrating this fragile foam into a dense base of egg yolk, milk, and flour. Standard mixing provides too much friction. Aggressive stirring mechanically shears the protein films, causing the captured air bubbles to disintegrate. Conversely, undermixing leaves heavy clumps of flour and yolk on top of the meringue. This unsupported weight eventually crushes the foam beneath it. This cross-section shows the goal of the folding technique. Gently scooping the heavy base over the foam suspends the air bubbles uniformly within the starch matrix without rupturing them. A successful fold achieves a physical equilibrium where the dense batter is fully supported by the buoyancy of the air. The cook portions the batter onto the pan in stages, piping it vertically to build height before the structure can spread. High heat causes the exterior to sear while the interior remains liquid. This temperature imbalance prevents the center from supporting the weight, leading to a total collapse. Sustaining this volume requires low heat, a sealed lid, and a small amount of water. This shows the transition as water converts to steam. The trapped vapor envelops the batter, ensuring thermal energy penetrates the center of the pancake evenly. Heat triggers a race between expansion and solidification. The air bubbles must expand at the exact moment the proteins and starches set to lock in the final shape. The pan functions as a thermodynamic expansion chamber, fixing the air into a permanent lattice the moment the structure reaches its peak volume. Lifting the lid reveals the final expansion as the remaining steam clears from the pan. The finished product is a tall, bouncy cylinder that retains its towering shape even when plated. As detailed in the Czech Journal of Food Sciences, managing these foaming properties involves precise control over conductivity and liquid drainage rates. Success is dictated by the chemical interactions identified in this peer-reviewed research. While associated with viral food trends, the physics required to produce this pancake remain unforgiving. Producing this result relies on aligning the variables of applied thermodynamics and advanced protein chemistry. Each bubble's lifespan is determined by the invisible physical forces of surface tension and air diffusion. This microscopic view shows the interlocking protein lattice flexing and rebounding. Mastering these physical forces allows basic ingredients to temporarily defy gravity.